Hi there, folks. Today we're going to be going all the way through section 3.8. We're going to be basically covering a hodgepodge of remaining topics related to derivatives. There's a lot of different things we can do with derivatives, and chapter 3 and chapter 4 really focus on the idea of the derivative and all the different applications. What we're going to be doing in the rest of chapter 3 is just a bunch of little applications. Chapter 4 is going to show the big application, which is optimization. And almost the entirety of chapter 4 focuses on the idea of how we can graph using optimization, how we can optimize rates of change or minimize or maximize if you prefer, as well as how acceleration plays a role in things. But as you can see for chapter 3, we have a little bit more of the chain rule to cover, in particular related to implicit differentiation. We then have exponential growth and decay, which is something you should already know about, the idea of how exponentials work. But your book actually does a good job of exploring it a little bit more thoroughly. I might recommend reading section 3.6 in addition to reading all of your other sections. You're all reading your textbook, right? But definitely read 3.6. And then also, we're going to do derivatives of things like the inverse tangent, as well as how to do linear approximations and Taylor polynomials. This is a tremendous amount of material, and so it might go a little bit long today. But let's just start with what we've done so far. So chapter 1 was all about functions and understanding how functions work. Chapter 2 introduced us to the idea of limits and continuity. And so far, chapter 3 has taught us about the derivative. Like I said, the rest of chapter 3 introduces strategies and applications. Then chapter 4 gets into the nitty-gritty applications. Chapter 3 is the how, chapter 4 is the why. And here's an example. Suppose that you have something which is weird. And for those who are going into biology and medicine, sometimes biology and medicine can get weird. And so here's an example of a graph. This is the graph of t sine of p1 plus p1 cosine of t equals 1. It is not a function, but it is an equation, and it is something which you could see. This is the type of system which you will encounter in the real world. And so the question is, what if we want to figure out what the rate of change is at a particular point on this graph? Clearly, we could find what it is because we could just draw the slope there. We could figure out what a tangent line might look like and then figure out what the slope of the tangent line is. But to actually calculate that slope is a little bit trickier. And that's where we're going to have a technique which will figure it out for us. The technique is called implicit differentiation. And so that's where we're going to start. And so the problem in the previous example used a technique called implicit differentiation. Implicit differentiation is basically where you take the derivative of something which is not written in explicit form. And so explicit form is y equals some function f of x. In order to do this, basically we're going to be taking the derivative of things which have different variables. And so let me break away from this and we'll just start playing with stuff. And so we already learned that if we do something like d dx of x squared, we would get 2x. Now, this x value here actually matters. This is saying we're taking the derivative of this function with respect to this variable. Now, here's the question. What happens if we did it with a different variable? What if we were to do d dt of x squared? Well, in this case, it really depends on how the x function and the t function are related to one another, which is where we get the idea of related rates coming up. For instance, let's suppose that we knew that x was a function of t. Let's suppose that x of t is equal to sine of t. Well, then when we do this, we could think of this as being d dt of sine of t squared. And that we can now take the derivative of. The derivative of stuff squared is going to be 2 times stuff. And then we have to multiply by the derivative of that inside bit, that sine of t, which would give us cosine of t. Notice with this though, what we just did was we said the derivative of the entire function, which would give us 2x, and then this cosine of t is going to be dx dt. We just used the chain rule. And when you see something like this, that's what we're doing. We're using the chain rule. This works no matter what x is. And so let's say that x were a different function. How about x of t is equal to natural log of t? Well, then we could say that this is equal to d dt of natural log of t squared, which we would know would be 2 natural log of t times the derivative of natural log of t is 1 over t. Notice again, in this case, this expression right here was 2x, and then this was dx dt. This will work no matter what. And so if we are not told what the function is, the derivative with respect to t of x squared is just going to be 2x dx dt. This dx dt comes out from the chain rule, just like it did here and here. And this works no matter what the variable is that we're dealing with. And so let's try another example. Let's say that we have d dx, and then let's say that we have sine of y squared. So when we take the derivative of this, as my voice starts to go already, we see that we have a sine function, and then we have a y squared on the inside, and then this y is a function of x. And so we start at the outside. The derivative of sine is cosine of y squared times the derivative of y squared, which is 2y. And then we need to multiply that by the derivative of y with respect to x, which would be dy dx. This is the answer. And so that's how you take the derivative with respect to other variables. And that's going to be very important because oftentimes we'll be dealing with something related to space or related to a population, and we'll be taking the derivative with respect to time. And when we do that, we're going to have all of these different variables floating around. And so when we go back to how we do related, or not related rates, implicit differentiation, we have to start by taking the derivative of each term in an equation, because we'll be given an equation which looks like this: t sine of p1 plus p1 cosine of t equals 1. When we take the derivative of that, we'll have to take the derivative of each term separately with respect to some variable. In this case, notice it's with respect to t. We do have to be careful though, because if we have the product of two things, like this example, ddt of y sine of t, well, that's a product rule. And so we would have to use the product rule in order to figure that out. You can write the derivative in the form of dy dx, dy dt, or just as the y prime. Either way is good. But do make sure that you're following all of the rules that you have already established. Once you've done that, algebraically solve for the derivative. And so usually there's going to be a y prime or a dy dx or dy dt, whatever you're dealing with, floating around. And when that happens, you just have to solve for that particular variable. And so I've got a few examples here. Let's take a crack at some of them. And we might do that first one, and then maybe we'll vary a bit. Notice I have the graphs there. You don't have to graph them, but it is fun to see what the graphs of these things look like. So let's do number 1, and then we'll come up with a random example. Sine of y squared plus cosine of x squared equals 1. And so if we wanted to find dy dx, well, first it might be important to actually know that that's our goal. So find dy dx. And so the derivative of the first term, sine of stuff, is going to give us cosine of stuff. So cosine of y squared times the derivative of y squared, which is 2y. Then times the derivative of y, which is dy dx. Plus cosine of x squared, well, the derivative of cosine of stuff is going to be sine of stuff, but with a minus sign floating around. The derivative of x squared with respect to x is just 2x. And we wouldn't have an extra term coming out of this like we did here, because that extra term would be dx dx, which is the rate of change of x with respect to x. And that's just 1. Finally, the other side, the derivative of 1 is 0. There we go. Now, that's the first step where we took the derivative of each term. The last step to find dy dx is we have to actually solve for dy dx. And that's just algebra. We would need to move this term to the other side, and then we'd have to divide by this term. And so if we move that to the other side, well, let's just do it all at once. We would get that this adds over. So it becomes 2x sine of x squared. And then dividing by this, we would get 2y cosine of y squared. We could simplify that. That's our answer. This expression will give you the rate of change of this relation, no matter where you're at on this relation. And so any point on the graph of this function or of this relation, this is going to be the slope. I kind of want to go and do that first example that I had listed up here, because it's a little bit more complicated, and I seem to recall I might have gotten the answer wrong in the notes, and it would be a good idea to double check that answer. And so let's double check that answer. And so the equation we have, and I'll say find dp dt, and we will make it t sine of p plus p cosine of t equals 1. I dropped the subscripts because we don't really need the subscripts. And so in order to take the derivative of this, what we would do is we would have to take the derivative of each part individually. And so we're going to take the derivative of this first term with respect to t, then this term with respect to t, then this term with respect to t. Notice, though, that each of these is a product, which means we have to use the product rule. And so the derivative of t with respect to t would just be 1 times sine of p plus t times the derivative of sine would be cosine. But because we're taking the derivative with respect to t, we would also get a dp dt that comes out. I'm just going to mark it as p prime to save room. Plus And so that was the first two terms. Now we have to do the same thing for the p cosine of t. Well, the derivative of p with respect to t would just be p prime. Times cosine of t. And then that's going to be plus p. The derivative of cosine of t would be a negative sine of t. So that is the product rule for the second one. And then on the other side, the derivative of 1 is 0 because it's a constant. Cleaning this up, I mean, we could clean it up pretty quickly, I think. Let's group our like terms together real quick. And so we will get a t cosine of p times p prime. Then it's going to be plus p prime cosine of t. And then we could say plus sine of p and minus p sine of t equals 0. The reason I grouped it that way is because now algebraically we need to solve for p prime, which means we're going to need to move these two terms over and then factor out the p prime and divide. So factoring out the p prime, we get p prime times t cosine of p plus cosine of t. And then moving this over, we get a p sine of t minus sine of p. Dividing now, we get p prime equal to p sine of t minus sine of p over t cosine of p plus cosine of t. So now let's double check with the notes, because I seem to recall I had the notes wrong at one point, and I don't remember if I ever changed that or not. So doing the old share screen, we have p sine of t minus sine of p over t cosine of p plus cosine of t. Looks like the notes are correct. So that is a good sign. You should always double check, because I do make mistakes every now and again. But that's the idea with implicit differentiation. What's interesting is you can actually use implicit differentiation to do some more interesting things. For instance, you can derive the natural log formula, as well as the inverse tangent derivative. And honestly, you can do all of the inverse trigonometric formulas using implicit differentiation. And let's show how. Let's start with the natural log formula, and then we'll do the inverse tangent formula. And so y equals natural log of x, and then we'll do y equals the arctangent of x. And so in order to derive the formula for the derivative of natural log of x, if we didn't already have the formula, and so we already know the answer to this is going to be 1 over x, but what if we had to prove that? Well, one way we could prove that is we could use what this natural log is actually defined to be. So remember that this is saying that e to the y equals x. That's how the natural log is defined. If we take the derivative of this thing with respect to x, then we would say, well, let's actually just write that out real quick so I can show you what that step looks like. We would say d dx of e to the y equals d dx of x. Well, the derivative of e to the y is going to be e to the y. But then since we're doing it with respect to x, we're also going to get a y prime, or a dy dx. On the right side, derivative of x with respect to x is 1. And so this tells us that dy dx is going to be equal to 1 over e to the y. And here's the fun step. When we go back, e to the y, we defined as being x. So that means that dy dx is equal to 1 over x. This is a very nice proof that the derivative of the natural log of x is equal to 1 over x. And it's usually the proof that I go with. The difference quotient definition proof is not very nice for this one. But this proof, that's nice. I like that one. And I believe there's a similar nice one for the arctangent of x. And so this was one I didn't have you memorize. But remember, if we're talking about arctangent, really what we're saying is that the tangent of y is equal to x. And so let's take the derivative of both sides with respect to x. So we want to do d dx of tangent of y. And we want to say that that's equal to d dx of x. Well, the derivative of tangent is secant squared, if I remember correctly. And so we will get secant squared of y times y prime. I'll just write y prime. On the right side, we just get 1. And so that tells us y prime, our dy dx, is equal to 1 over secant squared of y. Now here's the challenge. When we look at this, we started with tangent, and now we're ending with secant, and we'd really like to turn this secant back into tangent so that we could get everything in terms of x. Well, if you remember your Pythagorean identities from back in the day, sine squared plus cosine squared is equal to 1. If we divide everything by cosine squared, then we end up getting tangent squared plus 1 is equal to secant squared. That means that secant squared of y can be rewritten as 1 over tangent squared of y plus 1. And now we've got our tangent. And so y prime is equal to tangent squared, which is going to be 1 over our x squared plus 1. And that is the derivative of the arctangent. All of the inverse trig functions can be solved in a similar way. I think I removed all the homework problems related to the arctangent, but you can do this exact process whenever you encounter an inverse trig functions. And that's the idea behind implicit differentiation, which is the first big topic we have. The next one is the idea of related rates. And related rates are basically word problems that use implicit differentiation. And these that I have here aren't too bad. We'll do a couple of them. These things can get a bit abstract. In particular, as we're talking about biology and medicine. These are kind of the core ideas, though. And so let's look at them. This first example. Actually, before we do that, related rates are a type of word problem that typically involves developing a model relating two or more quantities, differentiating implicitly, often with respect to time, and then evaluating to find your desired solution. That respect to time is really the big thing. Almost always we're going to be dealing with rates of change with respect to time because that's how we are interested in rates of change. We're not interested in how one parameter is changing with respect to another parameter unless that parameter is time. Yeah, these are typically the problems that calculus students whine about the most. That's very true. That is very true. I'm sure I'm going to get lots of emails about related rates because every single problem is unique. And while the calculus isn't that bad, understanding the model can be very, very difficult. And as future biologists and medical professionals, you should recognize that that's going to be one of the biggest challenges you have, is trying to understand the models for what you're dealing with. But let's look at this first example. A 25-foot ladder is placed against a building. The base of the ladder is slipping away from the building at a rate of 4 feet per minute. Find the rate at which the top of the ladder is sliding down the building the instant when the bottom of the ladder is 7 feet away from the building. So right off the bat, we have an image, right? We have a building and we have some ground. I'll do some grass on the ground on my little image. I will make a little brick wall. There we go. And brick wall, brick, 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 brick. And then we have a 25-foot ladder. So let's see our 25-foot ladder. We'll do that in blue. All right. And what it says that the base of the ladder is slipping away. And so this is going to be slipping away from the building. And as this bottom is slipping away, well, this top part is going to be coming down the building. We're told certain values. And so we're told that the rate of change of this parameter is going to be 4 feet per minute. And so it's going to be going 4 feet per minute in this direction. We also know that this is 25 feet, and it is a fixed 25 foot. And then we're asked to figure out what happens when this bottom is 7 feet away. And so this base right here is going to be 7 feet. We won't be told what this value is, and what we're interested in is we're interested in figuring out how fast it is going down. And so what we really need here is we really need some variables, because so far we do not have any variables associated with this. And so let's just use x and y. And so in this case, we'll say that this is going to be the distance up, y, and we'll say this is the distance going across, x. Well, in that case, this 4 feet per minute is going to correspond to dx dt. And this rate going down is going to be related to dy dt. And what we're being asked to find is dy dt. And so there's our picture. What we need is we need a formula which relates all of this information. And in this case, we have a right triangle. We have 3 sides. And so our formula is going to be the Pythagorean theorem. And so our theorem says x squared plus y squared is equal to 25 squared. Now we have some options. And so the question is, do we want to figure out what y is, or do we want to figure out what dy dt is first? In the end, we're going to have to find dy dt. And we really want to bring everything back to the starting formula. What I might recommend is start by figuring out what y is, because that'll really help us firm up our picture. And so let's figure out what y is. And so if we know that x is 7 feet, we got 7 squared plus, I don't really need those parentheses there, plus y squared is equal to 25 squared. 7 squared is 49. This is 625. That would give us 576. I'm guessing that's going to give us a 24. But just to check, square root Square root of 576 is 24. And so we end up getting that y is 24. Note, technically, y would be plus or minus 24, but given the context of the problem, it's a positive 24. And so now we have to figure out what dy dt is. And the question is, how do we go about doing that? What some people do is they will use this equation here to do it. And that is bad. You would not want to use this equation where you've already substituted the 7 in, because this 7 is changing. And since this 7 is changing, we would need to use the original formula, the x squared plus y squared equals 25 squared. The idea being, if this ladder is shifting down, then it's only going to be 7 feet for an instantaneous moment. And to figure out rates of change, we need to see how it's actually changing. And so let's take the derivative of this formula with respect to t. That would give us a 2x dx dt, because we're taking the derivative with respect to time, plus 2y dy dt equals the derivative of 25 squared is 0. And so now we can take all of our values that we have and plug them in. And so we'll get 2 times x, which is 7. Dx dt is 4. Plus 2y, well, we know y is 24, times dy dt equals 0. And then our goal is to figure out what dy dt is. Doing the math, we got 2 times 28 and 2 times 24. And so we're going to get dy dt. It's going to be 28, negative 28 over 24, which is negative 76. And so our rate of change, this dy dt value, is going to be negative 7/6 feet per minute. And that's our answer. That is the rate of change at which the ladder is descending the wall as it's going out at a rate of 4 feet per minute at 7 feet. And so that's what a related rates problem looks like. Notice we started by just getting all of our information together. Once we had all of our information, we then tried to create an equation. And that's what this equation was. Once we had the equation, we took the derivative with respect to time, and that's what this step was. And then we just plugged in all of the different values that we had. The only thing that remained was the one thing that we were looking for. And at that point, we could algebraically solve for it. Almost all related rates problems are going to be something similar. Let's do one more real quick. And so for this next one, we'll do the rock thrown into a still pond. And I seem to recall this is a pond of molasses because the units I put on there are ridiculous. And so a rock is thrown into a still pond. The circular ripples move outward from the point of impact of the rock so that the radius of the circle formed by a ripple increases at the rate of 2 feet per minute. And again, 2 feet per minute, that's where we're talking about molasses and not water. Find the rate at which the area is changing at the instant the radius is 4 feet. So we need to create a model for this. And in this case, the shape we're talking about is a circle. And we'll pretend that's a circle. I'll make it bigger. There we go. It says the circular ripples move outward from the point of impact so that the rock, or so that the radius is increasing at a rate of 2 feet per minute. And so we'll draw our radius, and then we know that dr dt, which is the rate of change of the radius, is 2 feet per minute. Why I didn't go second, I don't know why. And then it says, find the rate at which the area is changing. And so find dA dt. The instant the radius is 4 feet. And so here's our video. Find dA dt. dr dt is equal to 2 feet per minute. R is equal to 4 feet. And we need a formula which relates area to radius, which is something we most certainly have. dA dt, or sorry, let's start with the area before we skip ahead. And so the area is equal to pi r squared. And that's one we know. And so let's take the derivative of this with respect to time. That would give us dA dt is equal to pi times 2r dr dt. Well, dA dt is what we're looking for. Pi is a number, 2 is a number, r we know to be 4 feet, and dr dt we know to be 2. And so we get dA dt is equal to pi times 2 times 4 times 2. 2 times 4 is 8. 8 times 2 is 16. The dA dt is 16 pi. And if we wanted the units, we're talking about rate of change of area. And so this would be feet squared per minute. Because again, it's molasses, and so it's going extremely slow. And so that's the idea with related rates. This next one, I give you an equation, and then you just have to find dc dx or something like that. And then this last one is talking about a spherical tumor. So you just have to remember the formula for a sphere. Oftentimes in your homework, it'll actually give you the equation because there are some really weird equations out there. One of my favorites deals with the photosynthesis, or how photosynthesis works. And so how does light get converted into energy? And can we calculate the rate of change of that? And so there's a lot of interesting examples that you'll see in your textbook and in the homework. But this is more just to give you the core idea about how to solve these things. One more example for how we can apply the implicit differentiation is logarithmic differentiation. The idea behind logarithmic differentiation is, what if we want to take the derivative of something of the form x to the x? It is not an exponential rule, it is not a power rule, and we don't really have the tools yet for it. Well, that's where implicit differentiation comes in. And so in order to find the derivative of something like x to the x, what we would start is we would start by setting or creating a variable y and setting y equal to this f of x. Then we can take the natural log of both sides. And after we take the natural log of both sides, we'll be able to use implicit differentiation to take the derivative of everything. And so let's start with the example of x to the x. I wanted to find the derivative d dx of x to the x. Like I said, we don't have the technique to do this straight away. We don't have a formula, I should say. But what we can do is we can set y equal to x to the x. And then all we have to find is figure out what dy dx is. And if we figure out what dy dx is, that'll give us the derivative of x to the x. Well, to do that, we can bring our x down using the natural log. If you remember your properties of natural log from chapter 1 or algebra 2, we can bring the x down and make it x natural log of x. We haven't taken a derivative or anything yet. We've just done algebra to it. But now that we've got it in this format, we can take the derivative of the left side. We can take the derivative of the right side. And so let's do it. The derivative of the left side, derivative of natural log of y, would give us 1 over y prime. On the right side, it is a product rule. And so the derivative of x is 1. Derivative of it'd be 1 times natural log of x. And then it would be x times the derivative of natural log of x, which would be 1 over x. Cleaning up the right side, we get natural log of x plus 1. And now we want to figure out what y prime was. And so we'd multiply both sides by y, giving y prime is equal to y times natural log of x plus 1. This still isn't quite the answer, though, because remember, originally our goal was to figure out what d dx of x to the x is, and there was no y in that thing. And so y prime, well, y prime, remember, is just d dx of x to the x. Y, we said, is x to the x. And then the natural log of x plus 1 just hangs out. And that's logarithmic differentiation. And so what we did was we started with something which we could not directly take the derivative of. And so we rewrote it as an equation, and then we took the natural log to bring that exponent down. And that's what this is. The exponent came down. We then took the derivative of both sides. And after taking the derivative of both sides, we ended up getting y prime equal to something in terms of y and x. But y we could convert to x to the x, and that gave us our final answer. Pretty much all logarithmic differentiation problems are going to follow this exact same pattern. And so let's just do a random one. These things can get weird looking. And so how about d dx? I want to do cosine of x, and I want to do it to the exponent power of e to the x plus sine of x. I have no idea what this graph looks like. I would imagine it is ridiculous. And let's see what it looks like before we even attempt the problem, because that's half the fun. So y equals cosine of x to the exponent power of e to the x, oh my goodness, plus sine of x. Yeah, I would say this is a very, very ridiculous looking problem. Yeah, it's just going to get crazy. It's undefined on an interval. Oh, that's because cosine goes negative. Yeah, that makes sense. And so you get this very, very abstract, weird graph out of this thing. On the left, it's a little bit more stable, at least. But let's see if we can actually calculate this. And so let's stop the share. There we go. And so in order to figure this out, we would start by saying, let's let y be equal to that stuff. And so y equals cosine of x to the e to the x plus sine of x. Now we would take the natural log of both sides. And so that's going to give us an e to the x plus sine of x times natural log of cosine of x. Well, on the left side, the derivative of natural log of y is going to be 1 over y prime. On the right side, we have a gross little product rule. And so the derivative of e to the x plus sine of x would become e to the x plus cosine of x times natural log of cosine of x. And then that's going to be plus r e to the x plus sine of x. And then the derivative of natural log of cosine of x is going to be equal to 1 over cosine of x times the derivative of cosine is negative sine of x. This term we could actually simplify by making it a tangent function if we wanted to. But now we've almost got our answer. We just need to bring our y up. And we already know that y is equal to cosine of x to the e to the x plus sine of x. And so our final answer is going to be d dx of cosine of x to the e to the x plus sine of x is equal to our y, which is cosine of x to the e to the x plus sine of x, times this whole mess, which is e to the x plus cosine of x times natural log of cosine of x. And then that is going to be minus e to the x plus sine of x times tangent of x. And so it's tedious, but there's nothing really difficult there. And so just make sure that you know your processes, and you should be able to go through this no matter what type of function you're dealing with. If we ever have a function with an exponent which is a different function, we can go through and use this process. You can also prove some really weird things using this. I seem to recall seeing, what's it called? The quotient rule was proven once using this technique. It's a very interesting way of doing it, but yeah. There we go. Here's some more examples. Honestly, I think the examples we just did were pretty dang good. And so we're probably good just with those. And here's one which is completely worked out. Let's make sure I did it right, because I don't trust my work. d dx of x to the cosine of x is x to the cosine of x, which gives ln of y equals cosine of x ln of x. And I think I see a mistake already, because the derivative of cosine is negative sine of x. So there should be a minus sign in front of this sine of x, which would mean there would be a minus sign in front of this sine of x as well. So definitely always double check my work. I do make mistakes on occasion. Exponential growth. And so this is getting into that section which I told you should definitely read, which is 3.6. And so 3.6 focuses almost exclusively on this idea of exponential growth. And it gives us this equation, this differential equation, which they call the law of natural growth. If we ever have dy dt equals ky, the solution to this is always going to be an e to the kt of some multiple. And looking at this, it's kind of a big deal. We'll actually focus more on it, I think, when we get to chapter 4. In chapter 4, we'll see how all of this stuff that we've been doing all the way through algebra and trigonometry all connects. And this is kind of introducing the idea. If we ever have the rate of change of a population as proportional to the population itself, the solution to this is always going to be an exponential. And one way to think about it is, what function is its own derivative multiplied by a scalar? And that function would be the exponential function, e to the x, or e to the kt. this type of an equation is called a differential equation, where we're saying the rate of change is equal to some function of the variables involved in that differential. So some function of y and t. We will deal with those in chapter 7 and then again in chapter 10. Chapter 10 would be if you take Math 356 next semester. Yeah, there's a tremendous amount of stuff to explore with differential equations. We actually have an entire course dedicated to differential equations and how to solve them. And like I've mentioned, the world runs on differential equations. And so a strong understanding of these is very, very valuable. But this one is very easy to solve. And 3.6 basically asks you to solve a number of problems using this fact. The solution to dy dt equals ky is equal to y of t, or gives you y of t equals y of 0 e to the kt. And so then it's just a question of, can you do that stuff? I put a note in here. It's basically section 1.4, but now it's structured in the language of derivatives. But the actual computational stuff isn't going to be that bad. And so I kind of just put it in here as a footnote. What I didn't put in as a footnote, though, is the idea of linearizations. And so linearizations, it's something that we've already done, but we also haven't. Linearizations are also known as linear approximations or tangent line approximations. And really what they are is they're just the equation of the tangent line at a point. And we know the formula for them because it's really just our point slope formula. The only difference is we move one of the terms over. And so when we think about point slope form, remember point slope form is y minus y1 is equal to m times x minus x1. Well, our linearization formula, and I'll put it over here to the side, is L of x is equal to f of a plus f prime of a times x minus a. Notice how similar those two are in that they are basically the exact same thing. If x1 would be our a, then y1 would be f of a. And it's just moved the f of a over to the right side. And then this slope, well, we have the language of derivatives now. That would just be f prime of a. And so this formula and this formula are exactly the same. And so when we're talking about linearizations, we're just talking about the equation of the tangent line. And this gives the type of problem you might expect to see. And so consider the function f of x equals the square root of x plus 3. And let's actually work through this one. F of x equals square root of x plus 3. Part A says find the linearization of f of x at a equals 1. And so first thing we're going to do is we're going to find L of x at a equals 1. And we can do that fairly quick, I hope. In order to do that, we need our a value, which we have. And so a is 1. We would need to know what f of a is. That's going to be f of 1, which is plugging 1 in. We get 1 plus 3 is 4. Square root of 4 is 2. And then we're going to need f prime of a. That's a little bit more work because we need to first find f prime of x, which this is a square root function. So it should be 1 over 2 square root of x plus 3. But then we need f prime of a, which would be 1 over 2 times 2, which is 1/4. And so that would tell us that our linearization L of x is going to be equal to f of a, which is 2, plus f prime of a, which is 1/4, x minus a. And let's double check. We have Desmos. Let's use it. So let's share the screen real quick. Go to our good friend Desmos. Our function was the square root of x plus 3. And if we did this right, we should get the linearization at x equals 1, which would be right here. And so our linearization L of x is equal to 2 plus 1/4. I am not good at typing today. X minus 1. And sure enough, those two curves meet at the point 1, 2. So now the question becomes, why do we care about linearizations? And here's the big reason why we care about linearizations. Sometimes the function we're given is not nice. And if we're given an equation which is not nice, maybe it would be easier to figure things out based on the linearization. And that's what the next thing asks. It says, use your linearization from part A to approximate 3.98 and 4.05. Are these approximations overestimates or underestimates? And so what this is asking for us to figure out what the square root of 3.98 is if we were to just use the approximation we just created, just using our linearization. And so for part 2, let's do the square root of 3.98 first. Oops, stop the share, there we go. Well, in terms of our function, that would be f of 0.98. What we would want to do is we would want to find our linearization to figure out what the approximation is. And so L of 0.98. And with that, we could just go to a handy dandy calculator. Handy dandy calculator says 2 plus 1/4 times, and then it's going to be 0.98 minus 1. And I end up getting 1.995. And so now the question is, how close is that to the actual answer? Well, if we were to do the square root of 3.98, that would give us 1.99. Then it is 499, 3734, and on. This 1.99499 is really close to 1.995. And 1.995 is honestly a nicer number to play with. And so that's the benefit of the linearization. It makes it so that it's a little bit nicer. And as you can tell, this was an overestimate because this is just a hair more than this thing. We could do the same for the other one. The other one was 4.05. And so the square root of 4.05, we'll just do it over here. Well, we would say that that's approximately L of 1.05. And then we could plug that into our handy dandy calculator. 1.05. And I end up getting 2.0125. Comparing that to the actual, the square root of 4.05. Square root of 4.05 is actually 2.0124618. And so again, That's pretty close. It's still an overestimate. And again, the benefit of the linearization is it's a much nicer formula typically than the formula that you started out with, because linearizations always become lines, and we can do a whole bunch of stuff with lines. The next one is, for what x values will the linear approximation be accurate within 0.5 units? Well, that's a harder one. What we could do is we could go to the graph because we want to figure out when the change in the y values is going to be less than 0.5. And so let's go up to our graph in Desmos. And we'll say this is our function. And so let's create a new function, which is the difference between our linearization and our starting function. And we'll call this the error, E sub RROR. There we go. And so this green curve is telling us how far off our linearization is. And we were asked the question, when is this going to be less than 0.5? And good old Desmos tells you right here. Everywhere between negative 2.657 and 8.657. That is when this error is less than or equal to 0.5. And so that's how we can play with our linearizations. As long as we're within that interval, we are going to be pretty dang close. And the fact that it's that close for that long, I mean, that's a very long stretch. Yeah, and that really highlights the value of the error. If we wanted it to be a smaller error, ooh, not that small, don't want a negative error. But let's say that we want it to be a 0.1 error. What's going to be within 0.1 on the interval from negative 1.13 all the way out to 3.93. So on that interval, it is still going to be very, very close, within 1/10. Cool. And so that's the idea behind linearizations. Linearization is really just a way of approximating a curve using a line. And that's all that it is. That said, we do have a few applications for it. The first one is Newton's method. And Newton's method is complicated. I tried to remove a lot of the Newton method problems from the homework, I seem to recall, because it is a very, very complicated process. And so suppose that you wanted to solve the equation cosine of 2x equals x. There is no way to do this algebraically. So try it, see what happens. You'll spend a lot of time trying to solve it. What we can do, though, is we can rearrange it by moving everything over to one side. So notice, to get this f of x equals cosine of 2x minus x, I subtracted the x over to the left side. And then our goal would just be to find the zeros of this function. And so here's the graph of cosine of 2x minus x. If we could find where this thing is equal to 0, meaning where it crosses the x-axis, that would give us the solution to this equation. Unfortunately, again, there's no nice approach to do that. But there is this thing called Newton's method. And as you can guess, it was made by Newton 500 plus years ago or so. And Newton's method is a way of approximating the zeros of a function using the derivative. The way you do it is you start with some initial guess, some just approximation for what you think the solution is going to be. And so in this case, I said, let's make a guess of 1. Clearly, based on the graph, that's a terrible guess because 1 is way out here. And so not a very good guess for where it's crossing. Well, if we took this guess and then we figured out where that point is located on the graph of this, then what we could do is we could create a linearization at that point and get us a line that follows that curve. And that line which follows that curve is going to then give us a point closer. Let me show you what I mean by that. And I've actually already developed a quick little app in Desmos, which will show it to you, which you can recreate if you want. And so let's start with the function that we're playing with right now. And so the function we're playing with is cosine of 2x minus x. Is that what it was? Let's go back and check. Cosine of 2x minus x. Yes. And so this is the function which we have. Let's start with an initial guess of x naught equals 1. And so this is our guess right here. Let me go home on this. There we go. And so if we start with an initial guess of 1, well, that's a terrible guess because we can see it's nowhere near where everything's crossing. But what if we took that 1 value and said, this is our guess, let's make a linearization at that point? Well, notice when we make a linearization at that point, it looks like it goes right through that point, right? It gets very, very close. And we can zoom in quite a bit on this. And you can see this blue line is where it's crossing. And this point right here is where the actual point is. And so that took us from being nearly 0.5 off to being very, very close. And so from this, we can get a new starting point. And so now if we repeat that and make this our new starting point, well, it's not quite the right point. And so we can come and get a new point up here and then create the linearization from this point. The linearization from this point is then going to get much closer. And I believe the linearization would give us this point. Well, what if we then took that point and we made a linearization from here? And so linearization from here then gets us much closer. And you can see how this is working. We're just getting closer and closer and closer. That last linearization would get us to this red dot here. And already we're talking about something which is ridiculously close. Yeah, looking at our scale, it's not even appearing on the screen because of how fine the scale is at this point. They're both saying 0.5149. But we can continue this, and I've made this thing here, which again, you can copy and paste if you want to, so that it repeats this pattern 6 times. And it lists what the approximations are at each step. And so our initial guess was x naught equals 1. Then from 1, we got 0.49756992047. And then we get x2 upon repeating that process, and x3 upon repeating that process, and x4 and x5 and x6. Repeatedly taking these linearizations ends up getting it so that x4, x5, and x6, the approximations, are accurate all the way out to here. That's 3, 6, 7, 8, 9, 10, 12 spots. And so it is accurate out 12 spots by the 6th time, or by the 4th time we've done this process. And that's what Newton's method's all about. Newton's method is a way of repeatedly doing this so that you get these really good approximations. What we're really doing, though, is we're taking the limit of a recursive sequence. And the linearization that we have, by the by, is this right here, y equals f of c naught plus f prime of c naught times x minus c naught. If we let this y value be equal to 0, since we're assuming that it's going to be where it's crossing the x-axis, that would give us the new approximation, because then we could solve for our, what's it called? Or sorry, we could then try and figure out what c naught, or what c value is going to give us that process. And so if we let y equal 0, then our next x value approximation would be given by this equation here, because we would just take the equation of the line and then just repeat it. And so what we're doing is we're taking this function here, c sub n minus f of c sub n over f prime of c sub n, and we're just repeatedly applying it over and over and over again. And we can do this no matter what function we have. And that's what Newton's method is all about. And so let's take a look. I have some practice problems down here. They're not nearly as interesting as one might hope. And so let's just play with this app that I quickly created. If we had sine of x, for example. Well, notice with sine of x, if we wanted to figure out where it's crossing, there's an infinite number of places where it's going to be hitting the x-axis. And so for Newton's method to work, we would really need to choose a value which is close to one of the particular values. If we chose something which was like at the very top, and so let's say that x is equal to pi over 2, for instance. Ooh, let's do pi over 2. Then notice that this blue line just goes on forever and ever and ever, and it actually never crosses. It's undefined for all of the values down here. But let's say that instead we chose 3.14. Oh, I don't have numlock on. How about 3.14? 3.14 over 2, I meant. There we go. At 3.14 over 2, our tangent line, our linearization at that point, ends up being so inaccurate that it doesn't actually cross until negative 1254, which is not a very good approximation. If instead we chose 3 as our starting point, though, we're able to quickly get to this 0 here. And we know that this 0 here should be close to pi. And looking at this, it gives us an answer very close to pi almost immediately. Our first linearization gives us 3.1425. The second one is 3.141592653. And by the time we're at x sub 3, we're at pi, or as close to pi as you would ever want. We could do this for other things too. And so let's suppose that we wanted to do the square root of 300. Well, the square root of 300 would be the solution to the equation x squared equals 300. And if we wanted to find the 0 of that function, we could do x squared minus 300. So if we take the function x squared minus 300, whoops, then notice over here, right now we're starting with an approximation of 3, which is a terrible, terrible approximation. And then this blue line is our first linearization. If we start closer, like let's say at 10 or square root of 300, that should be around 17. Let's say that we start at 17. Well, if we start at 17 as our initial guess, which is this value here, it gets to the actual value of the square root of 300 very, very quick. So notice the first guess is 17.323529. The actual square root of 17, or sorry, square root of 300 is 17.32050808. And yeah, by the time we get here to x sub 3, we're already more accurate than my calculator. And so that's Newton's method. You have a few problems in your homework, which is related to Newton's method. And I recommended that you use Excel, but honestly, using Desmos is just as good. I would recommend trying to derive where this formula comes from, though, because that's kind of a fun little exercise. The idea of if we know where our starting point is, can we figure out where our next value is going to be coming from? And that's a very fun little exercise. So definitely try and work through that. But that's Newton's method. The next topic is Taylor polynomials. And I believe Taylor polynomials are the last new topic for today. And so Taylor polynomials are the idea that sometimes a linearization just isn't good enough. And so what if we wanted to approximate something with a parabola? Or what if we wanted to approximate something with a cubic function? Well, it turns out we can do that. And the way we would do that is using what's called a Taylor polynomial. A Taylor polynomial is also known as a Maclaurin series, depending on what we're actually doing with it. But it's just a equation or a function which is accurate out to as many derivatives as you want. And so, for instance, if we wanted a Taylor polynomial centered at 0, what we would do is we would start with f of 0. And once we have f of 0, we would then say, well, what's the first derivative evaluated at 0? And then divide that by 1 factorial. Then what is the second derivative of the function? Divide that by 2 factorial. And then what's the third derivative? And divide that by 3 factorial. And so on and so forth, as far out as we want. Where these 3 factorials, first off, for those who aren't aware, what a factorial is it's where you multiply all of the numbers from that number down. And so if you were to do 5 factorial, that would be equal to 5 times 4 times 3 times 2 times 1, which is 2, 6, 24, 120. And so as you are creating our Taylor polynomials, we want them to match up to a certain number of derivatives. Well, what happens when you take the derivative of something like x to the 5th? Well, if you take the derivative of x to the 5th, you get y prime is going to be 5x to the 4th. If you do the next derivative, y double prime is going to be 5 times 4 x to the 3rd. Y triple prime is going to be 5 times 4 times 3 x to the 2nd. Y 4 primes is 5 times 4 times 3 times 2 x. And then y, the 5th derivative, is just going to be 5 times 4 times 3 times 2 times 1. And so this right here is that 5 factorial. In saying that we want a function which matches up to 5 derivatives, we have to first figure out what the derivative is at that value, or what the 5th derivative is. And then we would have to divide by this 5 factorial so that our term will match up. And let's see what this looks like for a few different examples. I've got the example e to the 2x here, and it says the Taylor polynomial of degree 5 at 0 is given by this expression. And so t5 of x is equal to e to the 0 plus 2e to the 0. Well, e to the 0 is just 1. I don't know why I kept that e to the 0 in there all the way. But it would be 1 plus 2 over 1 plus 4 over 1 plus 8 over, or plus 4 over 2 plus 8 over 6 x cubed plus 16 over 4 factorial, which is 24 x to the 4th, plus 32 over 5 factorial x to the 5th. And then it says just how accurate is this approximation? And again, let's go to our good friend Desmos. Let's see, here we go. And so let's start with just the function f of x equals e to the 2x. And we'll just zoom in a bit here just for fun so that we can really see the graphs of these. And so we'll start with our degree 0 Taylor polynomial, which would just be f of 0. And f of 0 is just 1. And just because I'm using t, it's not going to let me do that. So let me say f sub t, t0. Ooh, what if I do f, or how about this? T sub 0 of x. There we go. Making it of x made it so that it was a function. And this was what I wanted to see. I wanted to show you that this is what the approximation looks like. And so this is saying that this line is roughly the same as this function. And hopefully you can tell just by looking at it, they're not the same, not even close. Our level 1 Taylor polynomial, our degree 1 Taylor polynomial, t sub 1 of x, would be equal to f of 0, which we already know is 1. And then that's going to be plus our f prime of 0 over 1 factorial x. And like we mentioned, this f prime of 0 is really just 2. And so now the question is, how good of an approximation is that? Well, it's still not great. Let's do the next one. So t sub 2 of x is going to be equal to 1 plus 2 over 1 factorial. And honestly, we don't need to write the 1 factorial because we already know that it's 1. So really, we just write 2x. Plus, now this will be f double prime of 0 over 2 factorial x squared. Well, now notice it's getting a little bit more accurate. It's still not great, but it's at least hugging the curve a little bit. Well, let's just let this keep going. And so let's just say t sub n of x, because I don't know how far we'll go out with this one. We'll start with the 1 plus, and then we'll say f prime of x over, f prime of 0 over 1 factorial x plus f double prime of 0 over 2 factorial x squared. And let's add the third term, which would now be plus f triple prime of 0 over 3 factorial x to the third. Now that's looking like a really good approximation, at least on a short interval. Plus, let's see if Desmos is able to handle the exponent notation for this. F to the 4 of 0 over 4 factorial. Oh, it's unable to handle it. Let's see. F is a function. Yeah, it doesn't want that. That's a bummer. All right. And we will just do 1, 2, 3, 4. Oh, and it doesn't want that either. We need something before that symbol. Oh, come now. Let's say F 1, 2, 3, 4. That's weird that it's, oh, that's why. Cool. And so now we've got this one, x to the 4th. Let's do one more. Let's go to the 5th. F 1, 2, 3, 4, 5 of 0 over 5 factorial x to the 5th. So notice this is getting very, very close as we are near these values. And so while we started out with just a simple linearization, we've now found a way to make it so that the curves line up very, very closely. So this was t to the 5th. And we can compute these things for just about any function if we really want to. And so let's try it for sine. So sine of x, oh, and this 1 should be f of 0. There we go. And this should be f of 0. And this should be f prime of 0. And so this graph now is comparing the original function, which is in black, to the linearization, which is in blue, to the 5th degree Taylor polynomial, which is in purple. And hopefully you can see that these things, well, the blue one is certainly a good approximation on a short interval, but the purple one makes so that it's an approximation which is good for a very long time. Pretty much anywhere between -2 and +2, our Taylor polynomial degree 5 is going to be a good approximation. And the reason for that is all of the derivatives, or at least through the first 5 derivatives of this polynomial, match up with our sine curve. The further out we go, the more accurate it will get. And if you were to be taking Math 401, we would actually be talking about Taylor series. The idea being that if we did this out infinitely, we would get the exact same functions. And so if we did this infinitely, we could create a polynomial which has an infinite number of terms into a sine curve. And again, this works for other functions too. Natural log, it should not work for because it's undefined at 0. But if we made this a natural log of x plus 1, well, now we've got this purple curve matching up with our starting curve. And so here's our degree 5 Taylor polynomial. We don't need that one there. Let's say that we have an arctangent. Never get to play with that one. There we go. Notice again, it's not exact, but on a small interval, it is pretty dang close. And if we let this Taylor polynomial have more and more and more terms, it would get to be exact as we went out to the infinite. How about an arcsine? Never play with arcsine, especially not in this course. But notice how similar it is. And so again, the more terms we add, the more accurate it's going to get. And then we could say just e to the x. I mean, e to the x, that's the standard one. And you can see just how accurate it is. So that's the idea with the Taylor polynomial. The Taylor polynomial is a polynomial which matches up with your starting function up to a certain number of derivatives. And when you do that, you get things which are very, very accurate. The fun thing is that you can find a Taylor polynomial for any smooth function, and it's going to be a reasonable approximation on a given interval. Here's some practice problems. You know, there's nothing really that special about it. It's just saying find the Taylor polynomial degree 5 at 0. In order to do that, you really just need to calculate a bunch of derivatives. And so let's try. Well, none of those are that interesting. Let me create one real quick. And so let's do one by hand, and we will make it be f of x equals sine of 2x. And let's find the Taylor polynomial of degree 5 centered at 0. And so in order to do this process, what we're going to need is we're going to need all of the derivatives. And so we have our f of x. We're going to need to figure out what f of 0 is. And so let's just start by rewriting all of these. So f of x is equal to sine of 2x. F of 0 is going to be sine of 0. And sine of 0 is 0. Now let's do the first derivative. F prime of x is going to be equal to 2 cosine of 2x. Well, f prime of 0 is going to be equal to 2. F double prime of x, and so now we're taking the derivative of 2 cosine of 2x, is going to be equal to -4 sine of 2x. F double prime of 0 is going to be equal to 0, because sine goes to 0. F triple prime of x is going to be -8 cosine of 2x, which tells us f triple prime of 0 is equal to -8. And we need to do this all of the way out to the 5th derivative. And so now we're going to get -16 sine of 2x. 1, 2, 3, 4 of 0 is equal to 0. 1, 2, 3, 4, 5. So this is the last one. And it is going to be -32. Nope, I got a sign wrong there. This goes positive, this goes positive. There we go. Because the derivative of cosine is negative, and we already had a negative. So now this is going to be a positive 32 cosine of 2x. 1, 2, 3, 4, 5 of 0 is going to be positive 16. And so our formula for the Taylor polynomial of degree 5 is going to be starting with our f of 0 plus f1 over 1 factorial x plus f, or sorry, not f1, f prime of 0 plus f double prime of 0 over x. I'm messing everything up today, aren't I? Over 2 factorial x squared plus f 1, 2, 3 of 0 over 3 factorial x cubed plus f4, I'll just write the 4, of 0 over 4 factorial x to the 4th plus f5 of 0 over 5 factorial x to the 5th. Plugging that in, we get 0 plus 2 over 1x plus f double prime is 0 over 2x squared plus f triple prime is -8 over 3 factorial is 6 x cubed plus our 4th one is going to be 0 over 24 x to the 4th plus this 5th one is going to be a 16 over 120 x to the 5th. Cool. That goes away, that goes away, that goes away. So we are left with 2x minus 4/3 x cubed, 16 over 120. We could simplify that. 120 divided by 8 is 15. So this would be plus 2/15 x to the 5th. And so in theory, this function right here should be a very good approximation for sine of 2x. And let's see what the graph looks like. Let's see if the graph actually shows us that this is a decent approximation for our sine function. And so I'm going to hide this graph. I'm going to create this function to be our sine of 2x. And for a small interval, this should be a decent approximation. It's going to be let's just call it t of x. And it is 2x minus 4/3 x cubed plus 2/15 of x to the 5th. And it's not perfect, but when you look at it from this point to this point, it looks like a really good approximation. Let's put it in red so you can see the difference. I mean, it's not perfect, but as you look closer, it's a pretty decent approximation on that interval. And to compare, in theory, this should be the same thing as this graph, T5 here. Oh, no, it's not. Why not? That bothers me because these should be the same. And I wonder why they're not. I wonder if I got one of the terms incorrect. I can always just plug in the base terms in case I miscalculated. -4/3, 2/15. I guess we'll call that homework. See if you can figure out why these two are different from one another. Because in theory, they shouldn't be. And if anyone's able to figure it out, I will happily post that on a note on the video so that people can see what the difference is between these two and why they are not lining up exactly. That said, that brings us to the end of today's lesson. Today we covered a tremendous number of applications and things related to the idea of the derivative. We started with the idea of implicit differentiation, which allowed us to figure out the rate of change of functions like this, or things that aren't even functions, relations like this. And we used that to do a number of different things. We solved word problems called related rates. We then focused on the idea of logarithmic differentiation, which gave us the way to calculate things like x to the x. What is the derivative of a function with a function as an exponent? We then did exponential growth. And again, that's something which is definitely worth reading in your textbook. It starts introducing the ways in which we can use derivatives to understand how things grow and change. And then we went on to linearizations, and linearizations gave us a number of new tools, including Newton's method, which is a way of finding the zeros of any function, which in turn gives us the way of solving any equation, even things which cannot be traditionally solved using algebra, as well as the idea of Taylor polynomials. And Taylor polynomials gave us a way of figuring out a new, better approximation for our trigonometric functions. Using all these tools is getting us ready for some of the higher end stuff that's coming down the pipeline. In particular, we want to figure out how we can actually use derivatives to model things. And so, for instance, if we want to model how populations change or grow, or how they're affected by different circumstances, how does introducing poison to a system affect the population of rabbits and wolves? Well, we can't really understand that without giving them the poison, but we can create models which will represent it. And that's really what our goal is, to try and develop models to better understand applications in biology and medicine. And so that's what's coming. Next time, we will be working on chapter 4, which is mostly about optimization, as well as trying to understand graphing a little bit better. We'll learn how to model things using acceleration in addition to just where their extreme values are. But that will do it for today.